Now, in the context of the proceeding, we ask what will be the velocity of each ball when it reaches the end of its ramp. And we conclude very easily, since the ball starts at 0 and averages on the first ramp averages 40 centimeters d per cycle, then since the average velocity has to be the average of the initial and the final velocity is going to have to be double the average, 80 centimeter d per cycle at the end. Similar reasoning tells us that, well, since we start from rest and average is 30, then the final has to be 60, specifically 60 centimeters d per cycle. So those will be the velocities at the ends of the ramps, on the premise that the velocity changes in a linear fashion, straight line v versus t graph, and both accelerate from rest. Now, another way of understanding that reasoning is to look at the v versus t graph. V versus t graph for an object that starts from rest at t equals 0 is going to, well, you're going to have a graph that goes through the origin. It's going to be a straight line, and it's going to go from here to some final time and final velocity. So the coordinates of this point will be the time and the velocity when it reaches the end. So that this clock time here would be t sub f. I didn't mark that in, but it wouldn't hurt to do that. So let's go ahead and call that t sub f. And our velocity is v sub f. Now, our average velocity is 1/2 the final velocity, because to get the average velocity, we average the initial and the final. When we average two numbers, we get the number halfway in between them. And of course, the average velocity occurs at the midpoint of this line segment from the initial point to the final point, so that the time is also going to be half the time. So the clock time here is going to be I could say 1/2 TF at that point. We're going to use that to answer a couple more questions. We're going to use that picture as much as anything to answer a couple more kind of interesting questions. Okay, now we're to answer the question from the time between the release and the first ball reaching the end, what's the average velocity of the second ball? Now you want to think for a minute. The second ball hasn't reached the end of its ramp, so it hasn't had time to reach its final velocity. Okay, well, velocity of the second when the first is at the end, the time interval equals delta t1, which is 3 cycles. So the second ball requires 4 cycles to reach the 60 centimeter per cycle final velocity. So it is what? 3 cycles out of 4 cycles toward its end, which means it's 3/4 of the way there. Now, I don't like the way I stated that. It's not really 3/4 of the way there. It's 3/4 of the time required to get to the end has elapsed. So I'm going to change that statement a little bit. So we can say it's 3/4 of the way there time-wise, but that's a little bit of a clumsy way to say it. So I'm going to write a phrase in here. I'll do that off camera. And now I'll say that 3/4 of the time it requires to reach the end has elapsed. So its velocity is only going to have had time to attain 3/4 of its final velocity. Its final velocity is 60 centimeters per cycle. So its velocity is going to be 3/4 of that 60 centimeters per cycle, which is 45 centimeters per cycle. Now we can understand that also with a graph, and I promised a little graph. So I'm going to draw that off camera and then we'll talk about it. Okay, we're going to sketch a graph of velocity in centimeters d per cycle versus t in cycles, and the times will be 1, 2, 3, and 4 cycles, since 4 cycles is all we need to get both balls to the end of the ramp. Now both balls are going to start at the same, at the origin at time t equals 0, so both graphs will pass through the origin here. Now, what will the graph for the first ball look like? How are we going to label that graph? Well, it's going to be a straight line, and the first ball gets to the end in 3 seconds. So you should stop, pause a minute, sketch the graph that you think is going to work. Okay, well, here's 3 seconds, so the ball has to stop after 3 seconds. We don't yet have a scale on our velocity axis, so I can use any point I want to represent its velocity at 3 seconds, as long as the point is vertically above, and I'm saying seconds, the 3 cycle mark. So if this is the point on the graph and the straight line goes from here to here, then the velocity here has to be the final velocity on the first ramp. What's that? That's 80 centimeters d per cycle. Now, what does the graph that represents the velocity of the first ball from start to the final cycle look like? You should pause and draw that. And you should have already done that. Well, it's going to take 4 cycles, and it's going to average 60 centimeters d per cycle. So its graph is going to look something like this. Now, after 3 seconds, how fast is the second ball going to be moving? Right there is the graph of its velocity versus clock time. After 3 seconds, the velocity is going to be here. Okay? And it's going to be 3/4 of what it would be after 4 seconds, because you have similar triangles. Okay? You could think of the blue triangle here. I'll draw kind of a blue line along with the white line. So you got the blue triangle here, which has a length of 3 on this base, and the white triangle, which has a length of 4. So clearly, the sides of this triangle are going to be 3/4 as big as the sides of this triangle. Now, this side here is 60 centimeters d per cycle, so this side here has to be 3/4 of 60 centimeters d per cycle, which is 45 centimeters d per cycle. So just another way of visualizing and understanding that when the first ball reaches the end of the ramp after 3 cycles, the second ball will be at 3/4 of its final velocity. So now the question is, where is that first ball at the end of the 3 cycles? Well, it's going to be moving at 45 centimeters per cycle. It started at 0, so it went from 0 to 45 centimeter d per cycle in 3 cycles. What's its average velocity? Well, the average velocity on that interval is going to be correspond to the midpoint here. It's going to be half of the final velocity, because the initial velocity was 0. The average velocity is halfway between 0 and the final velocity. So its average velocity on the 3 cycle interval is going to be 22.5. We multiply that average velocity. Of course, I calculated it here. For delta t is 3 cycles, average velocity second ball is 0, plus the 45 centimeters per cycle velocity it's gained, and you divide that by 2 to average them, and you get 22.5 centimeters per cycle. So how far has the ball moved? Well, it's moved at this average velocity for 3 cycles. So we multiply its average velocity, 22.5 centimeters per cycle, by its 3 cycles, and we get 67.5 centimeters. Now, what fraction is that of the length of the ramp? Remember that the length was said to be 120 centimeters. So if you do 67.5 divided by 120 and reduce that, you're going to get the fraction. Another way of seeing it is that you've got 3/4 of its final velocity. In other words, 3/4 of it, the second ball, okay, is going to attain 3/4 of its final velocity. and it's going to have traveled for 3/4 of the delta T2, the 4 cycles that's required to get to the end of the ramp. So if you take 3/4 of the velocity for 3/4 of the time, you're going to get 3/4 times 3/4 of the length of the ramp, which is 9/16 of the length. And I've written a very similar statement here. The second ball travels for 3/4 of the time required to reach the end, averaging 3/4 the speed, because it only has 3/4 as much time to develop speed. So it travels 3/4 times 3/4, or 9/16 of the distance.